Welcome to the second week of the live interactive section for the course Engineering Mechanics. So uh, today also I will go through some demo problems which is related to the second week of the uploaded videos which already there in the website. So I hope all of you have already watched the videos. So I will solve some problems which are related to that particular topic. And I think I already you have been gone through the assignments for the second week as well. So there are some confusions regarding the assignment to some problems. So I will try to cover some of the assignment to problems at the end of the session. So basically I will go through some related problems. I will begin with some related problems. At the end I will touch up that confusion questions which are making some confusion. So let us start. So as I explained in the last week, so there will be two of such sessions every week. One will be conducted by me and another is will be done by one of my colleague. So we'll go through related problems for that particular week, which we expect you to come here already. I mean, be here. So after watching that week's videos, so it will be easier for you to follow. So in case if you have any doubt, so we will solve some related problems. In case if you have some doubt, stop us. So we'll try to explain those particular part clearly. And if you have any other doubts and not exactly related to the problems we are discussing here, I mean related doubts only related to that particular week or the previous weeks, you can ask. So I will give time for that, or you can ask before the session begins. So I hope now nobody has any questions, so we'll move to the first problem. So I want it to be, like I mentioned last week, I want it to be an interactive session. So every problem I will give certain amount of time for you to try it out yourself, and if you are able to find the answer, please put it in the chat box, or you can unmute yourself and say it loud. Then I will start explaining how we can actually proceed with the problem. So here is the first question. Specify the stability for the truss system in figure 1. The system is subjected to arbitrary non-external forces that are assumed to be acting anywhere on the truss. So notice that it's an MSQ, so one or more options may be correct. So just find it, that's all. So we have a truss system here. There are two support are there. Both are hinged support or pinned support. So it will have two reactions, horizontal and vertical reactions on both of them. That doesn't matter now, because it's just asking about whether it is stable, unstable, statically determinate or indeterminate. Actually these reactions will matter, so we will see. So I'll give some time for you to think of it, come up with the answer, then I will tell what exactly the answer and explain how we can. So I think it's a fairly simple one, you can try it out yourself, though I will wait for some time for first you to come up with an answer. Okay. So anyone got any answer? So let's go through this. So first of all, we'll count the number of links. So how many links it has? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So it has 15 links. A number of joins: 1, 2, 3, 4, 5, 6, 7, 8, 9. So if anyone notice any mistake, please inform me, otherwise I will be doing wrong things. So we need to evaluate this quantity 2j minus 3. So I hope already you have been watching the video, so you will have some idea why I am doing these things. So it's basically to determine the stability of the system. So here 2 into 9 minus 3, it's 15. So n equal to 2j minus 3. So such a system is actually stable and statically determinate, right? That will come to. Actually, it is internally stable and statically determinate. Now, that you can actually see if you have only triangles here. So each triangular piece is a structure. Actually a triangular component is basic element of a structure. So if you have just a triangle, it is stable. So you have triangles joined together, it is actually a stable structure. Just that here you have two supports, both are pinned joints. You have 4 reactions. So 4 reactions you have, which is R1, R2, R3, R4. But you have 3 equations because it's a planar structure, right? 3 equations is sigma. So here it's a R1, R2, R3 and R4. 4 reactions you have. 3 equations you have: sigma fx equal to 0, sigma fy equal to 0, and sigma m equal to 0, because it's a planar structure, truss system. So it's a planar truss system. So you have only 3 equations. So basically it is, in that sense, it is indeterminate. Degree of indeterminacy is degree of indeterminacy is equal to number of reactions minus number of equations, which is 1. So one of the reaction you cannot evaluate. So basically it's actually stable, but it is statically indeterminate. Basically it's an external indeterminate externally, but here there is no such option. So it's statically indeterminate, also it is stable internally. Externally also it is stable. So actually externally is over constraint. You have one more support reaction which is not needed at all. You would ideally have one pinned joint and one hinge joint. One pinned joint and one roller support for it to be statically determinate. So I hope that is clear. So anyone has any doubt in this question? It's actually fairly simple. Okay, then we will move to the next question. So I hope you are able to see the question options, everything. So in the structure shown in figure 2, so the length of all of the horizontal and vertical links are the same. Let's call it as some A. So this is A, 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 this is A. All are same. Select the correct options from below. One or more options might be correct. So it's showing there are 4 options. FAC is 3.53 kilonewton tension. That means in AC the force is 3.53 kilonewton and its tension. GE 3.53 kilonewton tension in member GE. So we have to find what is the force which is FAG sorry, FAC, FGE, and there are no redundant links in the system. That's the third option. We have to check whether there is any redundant link or not. And then FCG, which is this number, which is also we need to evaluate. So basically, three of the forces we need to evaluate to verify which of the options are correct and which of them are not. So see, it's an MSQ, it's a multiple solution question. So there can be more than one options which are correct. So so I'll give you some time for evaluate this and come up with an answer. I mean, at least try to evaluate FAC, FCG, FG, and see, and also check whether there is any redundant link in the system. Then after some time, I will try to explain. So if anyone found any answer like either FAC, G or CG, you could put in the chat box or inform me. You can use, so I hope already you know there are two methods you can use to find the reaction forces, sorry, not the reaction forces, the internal forces, FAC, FCG, FG and all. Method of joints, method of sections. You could use either of them, doesn't matter, but I suggest you to use method of joints to begin with. So later we will see in certain problems it is better to use a method of sections, and in certain problems you could use combination of both, method of joins together with method of sections. It will make it easier. So here I am giving a hint, you can go ahead with method of joins, and if you feel method of sections is easier, you could do it, that's all. So, anyone got answer? Either FAC, CG, GE, or anyone have found any redundant link? So let me explain. So we'll begin with the support reactions. So first of all, this has a hinge joint here, so it will have two of reactions. So a vertical reaction at A and a horizontal reaction at A. And at F, because it's a roller support, you will have only a vertical reaction at F. There will not be any horizontal reaction. Now actually a priori you can say there is a horizontal reaction at A should be 0 because there is no horizontal forces acting on the system. But better we stick to the convention. So we will first start with net horizontal forces. So this is external forces only. Okay. Now internal forces are coming into this picture. So internal forces, when I say FAC, you can see it's a tensile force in the member AC. I mean, it can be tensile force. We have to check whether it's a tensile force or a compressive force. Doesn't matter. It's an internal force. It will act on the body in both ways, so it will be cancelled. If you don't take a section, or if you consider joint A, FAC will act compressive or tensile force on A, on the joint A. On the joint C, the other end of the same link, it will do the other ways. It will cause a compressive or a tension force. So basically it's an internal force. It will cancel out in the whole in system whole as a whole. So this will you will have a better idea if you already watched the lecture videos. So anyway, if you have any doubt, please stop me. So I hope this is already you know this fact. That's why I'm just proceeding without going deep into this. Only we need to consider the external forces in this equation, in the equilibrium equation. Sigma Fx equal to 0. So you have only horizontal force A in the x direction. Let's say this is x direction and this is y direction. So which says horizontal force A is 0. There is no horizontal force. Now the sigma Fy is 0, which gives the vertical force Va is acting upward. Similarly, Vf is also acting upward, but 5 kilonewton is acting downward. So minus 5 should be equal to 0, or Va plus Vf is equal to 5. So this is one of the equation. We need to use that later. Now sigma moment about any point on the system should be 0. We could take moment about A. We can take a moment about G or F, doesn't matter. Finally we will arrive at the same equation, but every moment should be 0 for equilibrium. So if we use this as the equation, HA is already 0. Va does not make any moment because it's passing through the point A. So it will not, the moment arm is actually 0. So it will not make any moment. Now 5 kilonewton is actually A distance and it is making a clockwise moment. So 5 into A, I am taking clockwise as positive now. Vf is actually 2A distance from the point A. The moment arm is actually 2A, where A is some unknown distance, doesn't matter, which will be cancelled out, so that's why. Now it's anti-clockwise moment. So 2A times Vf is anti-clockwise, so the net moment should be 0. So it says that Vf should be 5 by 2. If you just do the calculation, 5 by 2 kilonewton. And if you use that in the equation 1, you will get Va is also equal to 5 by 2 kilonewton. So we have evaluated all the support reactions. Now we'll move to the calculation part. So first of all, see the link AB. So in the link AB, there is actually there should be internal force FAB. In the link BC, there should be internal force BC. Now let's think about joint B. At joint B, if you draw the free body diagram of joint B, you have FAB acting downward and FBC acting horizontal direction. Now if you just apply sigma horizontal equilibrium, so method of joint says that every joint should be in equilibrium. and because we are using the truss system, so we only need to use horizontal net horizontal force at the joint equal to 0 and the net vertical force at the joint equal to 0. We don't need to use the third equation, the net moment about the joint equal to 0. We don't need to use, because all of the forces are acting or passing through the joint. So yeah, it's a concurrent system. Every joint is a concurrent system in a truss system. So the moment is invariably, it's already 0. So we don't need to use the equation again. It should 0. So you can see joint B. Two forces acting, FAB and FBC. Both of them are passing through the same point B. So the moment arm for both the forces about the point B is already 0. So the moment about B is already 0. So we don't need to consider that again. Okay. So we'll proceed with the horizontal equilibrium condition, sigma Fx equal to 0. And you can see at B, only horizontal force is FBC. So that is 0. Okay. Now what about the vertical equation? Sigma Fy is equal to 0. That says FAB is the only vertical force, that also should be 0. Now you can see FBC is 0 and FAB is 0. So that means these two links don't have any internal force. So they are actually redundant links. So there exist redundant links in the system. So there exist redundant links AB, BC. Now we will see whether any other redundant link exists or not. But already two redundant links are there. They are AB and BC, because there is no internal forces on those systems. It's like redundant links are like, whether the link is there or not doesn't matter, because they are not participating in the loaded transmission. Okay. Now we know about FAB, FBC. So earlier, if you have a think about joint A, you have four unknowns, right? You have FAB was there, FAC was there, and in this link FAG will be there. And VA and HA we already evaluated. HA is already we have evaluated to gone to 0, and VA we already know. Just that earlier, before considering joint B, if you have considered joint A, then we had four unknowns, FAB, FAC and FAG. Now we have considered joint B first, and then we are moving to joint A. We already know FAB is 0. So now if we consider joint A, we have two unknowns, FAC and FAG. So can we evaluate two unknowns? Should be possible, because at joint A we have two equations. The horizontal net horizontal force should be 0, net vertical force should be 0, and also we need to we have two unknowns, so we already have two equations. So we should be able to evaluate both of them here. So let's see. So joint A. So joint A, if we draw the free body diagram, we have FAC acting like this. Okay, let me draw it again. So FAC is acting this way. See, the direction doesn't matter. You could have taken so right now I have drawn in such a way that in all the members or whatever I have drawn, it's already I have considered this tension is acting. I could have taken, let's say for example, in the member AC, I could have considered something like this, FAC. So this is compressive, representation of compressive force. Doesn't matter, finally we will get magnitude in the sense, the sign in the sense that if it is indeed compressive, then I will get positive in this sense of the direction. But if it was tension actually, then we will get the negative sign. So we will come back and say, okay, it was not compressive, it was tension. So that's what I am going to follow now. I will represent the force in AC or all other members. I am just going to blindly say they are tensile forces. Finally, when we get the actual result, if the sign is positive, okay, it was indeed it is tensile force. But if I get a negative sign, then I will say okay, it was not tensile, it's actually compressive. So this direction doesn't matter, just follow a single convention or some particular convention. So you can mix the conventions, just that you have to, I'm saying mix the conventions for different links. So let's say for AB you for AC you choose it to be tensile representation, you can choose AB for compressive representation. Just make sure when you take link A, you should put the arrow otherwise. So let me clarify. Let's say I had this triangle here, right? A here, then C here, then G here. So I chose to represent, if I chose to represent this is FAC, then when I draw the freeboard diagram of at the point A, joint A, I should represent FAC like this, and when I take the freeboard diagram of C, I should represent FAC like this. But instead, if I have chosen FAC to be the other way, which is the compressive way, if this was FAC, then the same thing I should follow here. In the freeboard diagram, I should have the directions like this. Excuse me. Or basically I should say like this. So just that you have to follow a particular convention for a particular link, that's all. In a different links, different joints, whenever you go to so because these are internal forces, right? According to Newton's law, they are acting on the same body, they will cancel. So let's see, we will come back to this joint A. So joint A has FAC and FAB is already 0, so we don't need to consider that. Now FAG is acting this way, and the horizontal reaction at A is already 0, we don't need to consider that. Now we have only this vertical reaction at A, which we already evaluated to be 5 by 2 kilonewton. Now what is this angle? Which is this angle. This angle is actually, so you can see the triangle has two sides, A and A. The hypotenuse should be A root 2. So basically it's a equilateral triangle, sorry, not equilateral, isosceles triangle with the sides A and A root 2. So you know the angle should be 45 degree here and here. Same is valid here also, 45 degree. So we'll use the fact that it's a 45 degree here. Now it's actually a system of concurrent forces here. So we could use the sine rule, sine of f1 by sine f1 by sine of alpha 1 equal to f2 by sine of alpha 2, or f3 equal to f3 by sine of alpha 3, or I can just choose to be using the which is basically final reduced form of the equation, or I can still use the actual equilibrium equation for joint A, which is basically sigma fx equal to 0. So for the moment I will follow this sigma fx equal to 0. In some particular cases I choose, or later I will choose to use the sine rule, which is easier actually. Everything is same only, finally lead to the same answer, just that. So okay, sometime it is convenient to use that simplified equation. So here let's say I will go through the basic. Sigma fx equal to 0. So we have FAC cos 45, which is acting horizontal direction, and FAG, which is also acting horizontal direction. They should balance to 0. And sigma Fy equal to 0 gives, so let's call this as equation 2. So sigma Fy equal to 0, we have VA acting upward. FAC sin 45 is also acting upward. So FAC Sine 45 is 0. So let's say this is third equation. So from the third equation, we can actually write FAC equal to minus VA by sine 45. Sine 45 is 1 by root 2, so it's minus VA times root 2, and VA is 5 by 2, so it's 5 by 2 root 2 is equal to minus 5 by root 2 kilonewton. So FAC, then I can say what is the value of 5 by root 2? Let me evaluate. Can somebody help me with this evaluations? Yeah, for this one I evaluated, it is 3.53 kilonewton, but we have a negative sign, so it should be compression. So which is one of the result. If you see the option, magnitude is correct, but it is given tension, so the first option is not correct. Okay, now we will again continue. So we have evaluated FAC, but using that, if you use the equation 2, you can evaluate the FAC. Sorry, you can use the fact that you know FAC to evaluate FAG. So let's see. So from equation 2, FAG is minus of FAC cos 45, which is minus FAC. FAC is already 5 by root 2, so it's negative 5 by root 2. So we have to follow the same, so we cannot just say that it is compression here in the equations. We have to just follow the sign convention properly here. So minus FAC is plus 5 by root 2 into cos 45 is 1 by root 2, so it's just 5 by 2, which is 2.5 kilonewton. So plus it's a tension FAG, but in the option there is no FAG. So why did we evaluate FAG? We may not need now, but we will need in the next step, where we are going to evaluate FG, right? FG and FCG. Okay, so till now everyone is okay, right? Any questions? Okay, so if no questions, we will move to the next joint. So right now we have evaluated FAC, which is given in the option. Now FGE and FCG is required. FGE is here, you can see here, and FCG is here. So both has a common point G, but for G, we do we know anything? So how many unknowns are related to the joint G? So we have FCG as an unknown, FGE as an unknown, and also if you see, this member has FGF. FGS is also an unknown. So 3 unknowns. FAG is also related to joint G, but which we already know. Now we evaluated FAG, 2.5 kilonewton in tension. So apart from that, 3 extra unknowns there. So we cannot just go to G and say to evaluate FGE and FCG. We have to follow some path. I mean, not exactly path, we have to go in such a way that we are able to, at a time there will be 2 unknowns in each joint, then only we can evaluate, because 2 equations are only possible to write for every joint in method of joint. So if now you can see joint C, FBC is not there because it's already 0. FAC is already known. Now FCG and in this member FCE are the only unknown. So 2 unknowns exist for the joint C. So we should be able to evaluate one of the unknown, FCG, which we require. So we will now go to joint C. So for joint C, if you draw the free body diagram, FC is acting like this, okay, and FCG is acting like this. and FAC is acting like this. In that, FAC is known, FCG and FCE are unknowns. Our objective is just to know what is FCG is. CE is not required. So once we find FCG, now we will use that information to go to joint G, where we now at this moment we will know FCG and FAG related to the joint G, which we can use to evaluate the force FGE and GF. GF is not required, only GE, but we can evaluate both at the joint G. So that's the plan. So first we will see what is happening in joint C. Now this angle is 45 degree, this angle is 90. Now, so like I said earlier, here I may use the sine rule. So because this is a 3 forces passing through a single point C, concurrent forces. Now what is this outer angle? We need that angle, right? So it's 360 minus 90 minus 45. So it's like 360 minus 135, which is 225 degree. Okay, so if we use the sine rule, so FAC, which is actually known, we will use the data later. FAC by the opposite sine of the opposite angle. So you can see FAC adjacent angles are 45 and 225. The opposite angle is 90. So it's sine 90. See, if you have doubt in this, please stop me. It's looking like concurrent forces, but one of the angle is actually bigger than 90 or bigger than 180 as well. So it may be complicated, but if you think, it's actually only 3 angles and 3 forces. It's a concurrent system. So you could just use the idea that one force and divided by the sine of the opposite angle. So FAC divided by sine of 90. Now we actually need F. So in this particular question, we need to evaluate FCG only. CE is not required, but we will write the entire system like the 3 equations together. So FCG by the sine of the opposite angle. Yes, anyone has any question? Somebody has raised a hand. Hello? Okay, I think that's a mistake. Okay, come back here. So FCG by sine of the opposite angle to CG. So FCG has adjacent angles 45 and 90. So the opposite angle will be 225. So it's sine of 225 equal to finally FCE divided by sine of opposite angle. So CE has adjacent angles 90 and 225. So the opposite angle will be 45. If I use that information, sine of 45. So our objective here is just to evaluate FCG. So from this expression I can just write FCG is equal to, just rearranging the first 2 times here, sine of 225 by sine of 90, which is just 1, times FAC, substituting the values. So what is sine of 225? So you can write it as a 180 plus 45. So then you can see sine of 180 plus 45 will be minus of sine 45. So it will be minus 1 by root 2. By sine 90 is 1 times FAC. FAC we already know, it is actually minus 5 by root 2. So that minus and this minus will make it plus 5 by root 2. So we'll have plus 2.5. So we have evaluated FCG to be 2.5 kilonewton. So if you come back and see FCG is 2.5 kilonewton, it's given in the option, and it's a tension because it's mandatory we got, plus we already taken the convention plus to be tension. So the option 4 is correct actually. Okay. Now we had to check FGE, that's the only remaining force in the option that we need to evaluate. So let's come back to so for to evaluate the force FGE, we need the joint G. So let's see joint G. What are the forces in joint G? So if you see joint G, so there is FAG is acting in the left direction and FG is acting at 45 degree. So which is an unknown, we have to evaluate. FGF is acting horizontally and 5 kilonewton is acting vertically down, and then FCG is acting upward. Okay, so this angle is 45 degree, this angle is 90. So this is the point G about which all the forces are drawn. Now here GE and GF, these two are unknown forces and all other forces are known. FCG and FAG are already known. So this has actually two unknowns only. So we have two equations as well. So we can ideally solve this. So if you have, actually observed, we can reduce this to only a 3-force concurrent system in such a way that you can write the resultant of FAG and GF because they are just opposite forces. Similarly, 5 and FCG, then it will be reduced to a concurrent system. That will be easier way to do it. Like you can write like this. So 5 minus FCG because they are just opposite forces, and you can write FGF minus FAG, they are also opposite forces. Then FGE is acting this way. Now this is the easier way to do, or you can apply sigma fx equal to 0, sigma fy equal to 0, then solve them simultaneously to obtain GE and GF. Our objective is only evaluate GE. GF we will anyway get from those equations additionally. We don't need that because in the option only G is given. So I will go ahead with this simple this method. So if you have any question in this conversion, please stop. I hope it's pretty basic to understand. Basically I am saying that FGF and FAG, they are opposite forces, so I am resulting them writing FGF minus FAG, and I am putting arrow on the right hand side. Doesn't matter if I get the negative sign. Okay, I will realize that okay, it was not in the opposite direction, it was actually in negative direction. I'll just go with the convention and see whether what sign I am getting and all. Okay, so this angle will be 45 degree, this angle will be 90. Like earlier, this angle will be 225 degree. So using sine rule, again I will write the force at GE, member GE, by sine of the opposite angle, which is 90 degree, is equal to FGF minus FAG by sine of the opposite angle, which is 225, is also equal to 5 minus FCG by sine of the opposite angle, which is 45 degree. So now our unknown GE we need to evaluate. CG is already known, we have evaluated FCG. So we can use the first and last combination to write FGE as sine 90 by sine 45 times 5 minus FCG. So sine 90 is 1, sine 40 is 1 by root 2, so the combination will make it root 2 times 5 minus FCG. FCG we have just evaluated, it is 2.5 kilonewton, or 5 by 2 plus 5 by 2, so it's 5 by 2. Now you will see it's 5 by 2 times root 2, which is 5 by root 2. So it's plus 5 by root 2 kilonewton. So we have seen FGE is 5 by root 2. I think we already evaluated, it is 3.53 kilonewton. It is in tension because the sign came up with the plus, right? So FG is in tension, 3.53. So FGE 3.53 in tension. So second option is also correct. So the third option, there are no redundant links in the system. There exists redundant links, right? You can see AB and BC are zero force members, so they are actually redundant. So the option C is so wrong. Option A, we already seen FAC is 3.53 only, but it's compression. So the option A is also wrong. So only second and fourth option is correct. So any question? So we have completed this question. Any doubt in this? Okay, so if no doubt, we will proceed to the next question. So find the force in the link BC. Where is link BC? Yeah, here link BC. Let's say this is FBC. So we need to evaluate what is the force in link BC of this particular system. Various options are given. So I will give you some time for do it yourself. Then I will explain how to do. So here all the triangles are isosceles. Equilateral triangles of side 5. So you know what is the angle. This is 60 degree. This is 60 degree. This is also 60 degree. And E is a pinned joint. And yeah, so nothing is given about this point, right? So you can think it as, for the moment, it's not a link, it's a rope, so it will only carry some tension. You can call that tension as T and try to do yourself. Don't think of the reaction. So it will have some reaction force, it may have, but if it's a rope, that doesn't matter for one. It will only transmit a tension. For the link E, you can have a horizontal and a vertical reaction. So let's say the horizontal reaction is HE and vertical reaction is VE. So try to yourself and then I'll explain. So anyone found the answer? So here also you could use only method of joins. It's a hint. Okay. Method of section is not needed here. But if you feel you can use it. I am just saying it's enough to use method of joins. See, every problem you could solve purely by method of joins or purely by method of sections or a combination of both. Just this is ideally it should be possible to do it. Just that certain problems will be more easier if you use method of joins, or certain other problems will be easier if you use method of sections. That's only difference. Other than that, concept is same, just the equilibrium of sections or joins. Final answer will be the same. Some problems using one method will be faster, the other method will be slower. You have to do a lot of things. So here we only need to evaluate the force in the member BC. So you could consider joint A first, then B. That itself is enough. A and B is enough, I think. Or you can go A, C. No, C is not possible because C has extra links, so that will be difficult to do. Or you could take a section which is passing through the link BC, cutting at some point at BC, then the force at that link is BC. That also you can try, but I think method of section is a little complicated. Join will be easier. So anyone got answer? Okay, so let me explain. So if anyone found, you can put in the chat box. So first of all, we need to evaluate the external forces. So here the reactions are horizontal force at E and vertical force at E, because E is a pinned joint, and then as I mentioned, the tension in the rope T. So these three forces are unknown. Okay, so let's see what is this angle. So this angle is 60 degree. We need that angle, right? Because to write the equilibrium, we need a horizontal and vertical component. So for that we need that angle. So if this is 60 degree, then this is also 60 degree. So if that is 60 degree, this should be 30 degree. So we can split the tension into two components, T cos 30 and T sin 30. Okay, so now sum of the horizontal forces should be 0. So sigma fx equal to 0, which gives T cos 30. This is only the external forces we are considering. T cos 30 is acting horizontal direction, positive x direction. HE is acting in the horizontal force in the E is acting in the negative x direction. So they should balance. So that's an equation. But both HE and T are now unknowns. We'll come back to it. So this is one of the equation. Then second equation is sigma Fy is 0. Now we have vertical E is acting upward. Then T sin 30 is also acting upward, right? So plus T sin 30. Then 30 and 20 are acting downward. So minus 30 plus 20 should be 0. Now sum of the moment about some any point should be 0. So I could take any point, but let me choose a moment about E equal to 0. It says that the horizontal reaction at E and vertical reaction at E don't have a momentum, so about E, so it will be 0. They will make moment 0 about E. Then 20 kilonewton is acting 5 meter, so 20 into 5 will create a moment, but it is an anti-clockwise moment. Let me take anti-clockwise as positive. 30, which is actually 10 meter apart, so that also going to make an anti-clockwise moment, so 30 into 10. Now T cos 30, which is actually acting this much unit, what is that distance? It's actually this angle is 30, so it's actually 5 cos 30, and this is going to make a clockwise moment, so it is minus T cos 30 into 5 cos 30. Now T sin 30, which is actually this much unit apart, which is, this is the distance, which is actually so if this is 5 cos 60, so that is also going to make a clockwise moment. So I can say it is T sin 30 times 5 cos 60. So this entire moment should be 0. So I can rewrite this equation as 20 into 5 is 100, 30 into 10 is 300, so 400 on the left hand side, and bring all the tension related terms to the right side. So it's 5 into T cos square 30 plus sin 30 cos 60. So you can say cos 60 is actually sin 30 only, so it's sin square 30. So 5t is equal to 400, because sin square 30 plus cos square 30 will be just 1, or tension is just 400 by 5, which is 80 kilonewton, 30 into 300 plus 100. Yeah. So this is the tension acting on the string. Now if you use that back in the equation 1, so from 1 you will get horizontal reaction at E is just T cos 30, which is 80 into root 3 by 2, so which is 40 root 3 kilonewton. And vertical reaction at E from the second equation, which is 50 minus T sin 30. So 50 minus T is 80 into sin 30 is 1 by 2. So 50 minus 40, which is 10 kilonewton. So we have evaluated all the support reactions: horizontal reaction at E, vertical reaction at E, and the tension on the string. Any question? So now we will move to evaluating the internal forces. So let's see first joint A. Start with joint A. So why we are starting joint A is, joint A has two unknown forces, FAB and FAC. Our objective is to evaluate FBC. For that we have to either consider joint B or joint C. Okay, but if you directly consider joint B, which has unknowns FBC, FAB and also FBD, three unknowns, but only two equations are present for joint B, so you won't be able to evaluate that at that present moment, because you don't know any of the, at least if you know one of them, then you can evaluate the other two, because only two of them you can evaluate at the moment. Similarly, for if you directly consider joint C to begin with, you have unknowns f a c b c, and here you have f c d, then f c e, four unknowns. So only two you can evaluate at the moment, so it's not possible. That's why you are starting from A, joint A, where two unknowns are there, FAC and FAB, and two equations you have, sigma fx equal to 0 and sigma fy equal to 0. So you will be able to evaluate both of them if you begin from A. Then we use one of the information to pass to the next joint, then evaluate the unknowns in that joint. Starting with joint A, we'll draw the Freiburg diagram of joint A. We have 30 kilonewton acting vertically downwards, and an unknown force FAC, and another unknown force FAB, and this angle is 60 degree. So you could either use the sigma fx equal to 0, sigma fy equal to 0 to evaluate this kind of an arrangement. I simply going to use the sine rule because that is easier. But if you want me to use the sigma fx equal to 0 or sigma and sigma fy equal to 0, that particular or the basic form, just stop me, then I will do that. Otherwise I am just going ahead with assuming that you are familiar with using this sine rule. So just we need all the angles. So 30 degree, sorry, there's no 30 degree, 60 degree, 90 degree, and the remaining angle will be 360 minus 60 plus 90, which is 360 minus 150, right? So which is 210. So if I use the sine rule, so FAB by sine of the opposite angle. So adjacent angles are 210 and 60. So the opposite angle will be 90 degree. Now FAC divided by sine of the opposite angle, which is 210, equal to 30 kilonewton by sine of the opposite angle, which is 60. Now we have two unknowns, FAB and FAC. Both of them can be evaluated, but right now we are first evaluating FAB, then we will pass that information to joint B. So ideally we don't need to evaluate FAC for the moment, but we could evaluate. So let me write FAB. So that is considering first and last equation only, which is sine 90 by sine 60 times 30. Sine 90 is 1, sine 60 is 1 by 2, so we will get it is 60 kilonewton FAB. Oh sorry, sine 60 is root 3 by 2, I made a mistake. Yeah. So it's 2 by root 3 times 30, so 20 root 3 kilonewton. So if anyone notice any mistake, please inform me, otherwise I will be going with the wrong values. Okay, that is FAB, and this has positive value, means it's in tension. Now we'll move to the next joint, that is joint B, where so if you draw the Freiburg diagram, you can see FAB is acting in this way, which we right now evaluated. Now FBD is acting this way, and FBC is acting in this way. So here we know what is FAB is, just we evaluated now. FBD and BC are unknowns, which we need to evaluate. And if you see the angles, this angle is 60 degree, which is the from the triangle, and again from the triangle this angle is 60 degree, and the remaining angle is, so if you subtract 120 from the 360, so you should get 240, I think. Yeah, so it's 240. So this is joint B. So again I am going to use the sine rule, because this is a system of concurrent forces, 3 forces acting. You could in principle use sigma fx equal to 0, sigma fy equal to 0. I hope you guys know how to do that. If you want, like I said earlier, detailed calculation with a sigma fx equal to 0 and sigma fy equal to 0 for the joint B, please inform, I will go with that. Otherwise I will just keep that, insert the sine rule, which is the easiest thing I think here. So just FAB by sine of the opposite angle, which is here it is 60 degree, equal to FBD by sine of the opposite angle, which is also 60, and FBC divided by sine of the opposite angle, which is 240. So we know what FAB is, we can evaluate what FBD and FBC is, but in the question is asked for FBC only. So I will just use the first and last equations to evaluate what FBC is. BD is not required, that's why I am just keeping it. So FBC is equal to sine of 240 by sine of 60 times FAB. Now what is sine of 240? 240 is 180 plus 60, right? So sine of 180 plus 60, which is basically minus sine 60. So minus sine 60 by sine 60 into FAB. So it will be just minus FAB, which is negative of FAB. We have already evaluated, it is 20 root 3 kilonewton. So it's negative 20 root 3 kilonewton. So FBC is equal to 20 root 3. So if I evaluate 20 root 3, it's 34.64 kilonewton. Because of negative sign, we should say it is compression. So do we have option? Yeah. So option A, 34.64 kilonewton in compression. So that's the answer for this question. So any doubt in this? Is it clear? Any part need to be explained better?
No, sir.
Good. So then we'll move to the next problem. Determine the maximum value of the force F which can be applied such that none of the members are subjected to forces more than 5 kilonewton in tension or in compression. Options are given: 1.18, 3.54, 2.5, 1.77. So I hope the question is clear. So we have a structure which have a lot of members. F is a force, it's let's say call this as A, B, C, D and E. So we have joints A, B, C, D, E. At A there is a force F is acting. So we have to find F, the maximum value of F, such that none of the forces, either compression or tension, in any of the member will not cross 5 kilonewton. So I hope the question is clear. So you could try yourself, and if you found the answer you can put in chat box. So I will give some time, then I will explain how to do it. Same procedure only, just right now F is not given, so you have to evaluate everything in terms of F, every internal forces. Then whatever is the maximum internal force, you can just say its value should not cross 5, and accordingly you can say what is the limit for the value of f. Okay. See, if you think I don't need to explain this question, or I am going very slowly, or I am going very fast, you can just give me some feedback so that I can adjust to accordingly. This is actually a fairly simple problem, but some may feel this is difficult, some may feel very easy. Whatever your feedback, I am welcoming that. Please inform me, so according that I will change my mode of teaching. Any response? Anyone has any found something, at least reaction in, sorry, not any reaction forces or internal forces, AC, AB, BC? Okay, so let me go through this. Meantime, if anyone found the answer, please put in the chat box. We will discuss that. So right now we have C2 support, E and D, both are pin joined. So there's an issue because now it is over constraint in the sense of we have four unknowns. Reaction forces, which with the three equations we cannot solve all of them. So there's an issue with the support reactions. So for the moment we will just forget about it. We'll come to that. Right now actually we don't need that to solve this problem. We only need the internal forces. We don't need support forces. So we'll start from joint A. If you apply the same rule, so so for joint A, you have F is acting. F is an unknown. We have to evaluate F, but we have to evaluate all other internal forces, for example FAB and FAC, in terms of this unknown F, and check what is their maximal limit, and that limit should not cross 5 kilonewton. That's the criteria. So for joint A, if you see, we have F is acting here, FAB is acting here, and FAC is acting here. Okay, so we just need, we can like earlier I am going to use the sine rule. For that we need the angles. So I will just divide it like this. Now you can see, let's say this angle is theta 1, So this is basically an isosceles triangle, theta 1, and the same theta 1 will come here, or let me call that as theta itself, theta, theta. So from the triangle you can evaluate what is sine theta. Sine theta will be opposites. Okay, let me evaluate the tan theta, that will be easier. So tan theta is 1.5 yeah, so this is 1.5 given, and this is also 1.5. So tan theta is just 1, so that means theta should be 45 degree. Okay, so theta is 45 degree, so 2 theta is 90 degree, so which is this angle. So this is actually 90 degree, and what is this angle? So for that we let's say this angle is phi. If you see tan phi, which is 1.5 by, which is the opposite side, this, which is 1.5, and the adjacent side is also 1.5. Okay, so tan phi is also going to be 1, so that means phi is also 45 degree. So this angle is 45 degree. Then this angle going to be 360 minus 135, which is 225 degree. Okay, now we use a sine rule. Sine of f by sine of the opposite angle, which is 90, equal to FAB by sine of the opposite angle, which is 45, equal to FAC by sine of the opposite angle, which is sine of 225. Now you can write FAB using the first two together as sine 45 by sine 90 times f, which is just f by root 2. Now FAC is sine 225 by sine 90 times f. So sine 225 is minus 1 by root 2. So it's minus f by root 2. So we have evaluated two forces, AB and AC. Now we can use this information in joint B. So if you see joint B, now we have one force FAB, which is known, and here FBC, which is unknown. Okay, joint B has some limitations because we have three unknowns coming here. FBD is also an unknown, and FBE is also an unknown. So we cannot just directly pass to joint B. So we should ideally go to another joint, which is joint C. So from A to joint C we can relate. In joint C we have unknown FBC, another unknown FCD, another unknown FAC. FAC is known because we have just evaluated what FAC is. So we will use that information. With the angles you can see this angle is going to be theta only. 90 minus theta, because it's a right angle triangle. This angle is theta, so it should be 90 minus theta. Theta is 45, so it will be 45 degree. And this angle, similarly, you can say it is also 45 degree. So you can just use that information, 45, so that is 90, and this angle will be 270. So using that information, you can evaluate what is FBC and FCD. So I hope this is easier to do. I will just write the solution, what is FBC, what is FCD and all. So you can just follow this procedure for every link. So from C you can go to D, from D you can move to B. Like that you need to evaluate. You don't need support reactions for it, you only need the internal forces. So let me write the solution. So FBC you will find it to be F only, plus. And
So there we need to just we have to use the sine rule, right, sir?
yeah, you can use sine rule, or you could, ideally you should basically use the sigma fx equal to 0 and sigma fy equal to 0. Just that sine rule is like, if you do this same thing, you will get the sine rule again, because it's a concurrent system, three forces are there, you can basically sine rule, get the same result. uh, so every joint you have to use either sigma fx equal to 0 and sigma fy equal to 0, or sine rule, which one you think is easier for you. I am just using sine rule because that is easier for
Okay,
me.
sir.
Every joint you have to use
Okay,
that.
sir.
Make sure you have only two unknowns in every joint. So as I mentioned earlier,
Okay,
b
sir.
we didn't choose b because there are three unknowns, so we cannot solve. In c, if you choose c at this moment, we have only two unknowns, that's why we are going to c. Once you're done with c, we could either go to b, because once you're done with c, you will be known what is fbc, and already you have evaluated what is fab. So if these two are known, then only unknowns in joint b is fbd and fbe, which you can use sine rule or the equilibrium equations to evaluate. Or when you're done with c, you can move to joint d, where also you'll have only two unknowns. Actually not two unknowns, you will have support reaction also, so you better go to joint b. But support reaction also, because support reaction is an unknown here, that's a little issue, but you can gradually proceed from one joint to another joint to evaluate all the internal forces. So I'll just write the solutions. fbc is just f. Now you have fcd, you will find it to be minus f by root 2. Then fbd, which is also minus f by root 2. fbe, you will find it is f times root 2 plus. Then finally fed, which you cannot evaluate at this moment, because uh, you have two support reactions, so fed can be related to, so basically if you assume that there is a vertical reaction, a horizontal reaction at d and a vertical reaction at d, then you will find the force fed should be equal to vd itself, the vertical reaction at d, which you cannot evaluate explicitly, because there are four unknowns in terms of the support reactions. You have a horizontal E, and a vertical E is also there. So in that sense, you cannot just evaluate FED that simply. But remaining forces, if you see all the remaining links, the maximum force you can see it is F root 2, and the minimum force is F by root 2 in all the links in terms of magnitude. So we just need the maximum force, and it is given that the maximum force should be less than 5 kilonewton. That's given in the question. So for that to happen, F should be less than 5 by root 2. Or what is 5 by root 2? It's 3.53. So F should be less than 3.535, so 54 kilonewton. So option B is the correct answer. I hope that is clear. Any question?
No, sir.
Okay, so we'll move to the next problem. Select the zero force links for the given loading. Multiple options may be correct. So it's actually fairly easier one. So I'm not giving any time. If you find the answer, tell me. Or let's say which are the numbers you think is zero force numbers, zero force links.
Sir, the fourth option.
Can you repeat? Oh, you're
Sir,
saying
the
option
answer is
option
fourth option.
option 4 is correct. That's what you're saying.
No, no, I'm not sure, sir. Just guessing.
Okay, okay, we will see. We will see. Any other suggestion? So, zero force links means there is no force in that link, or the internal forces are zero. In a previous problem, I have shown an example having zero force members. So, we will go through each of the member. Let's say in the option 4, CH. Where is CH? Yeah, CH is here. This is a CH member. So, if we consider joint C having, okay, let us draw joint C here. It will have FBC acting this way, FCD acting this way, and FCH acting this way. Now we have a concurrent system of three forces. Okay, this is a 90 degree, this is 90 degree, this is 180 degree. So if you apply the rule, FBC by sine of 90 is equal to FCH by sine of 180 is equal to FCD by sine of 90. So if you, so all of them are unknowns, we can write two forces in terms of the other force. Let's evaluate what is FCH, the force in the member CH, which is, just use the first two together. It's a sine 180 by sine 90 into FBC. Now sine 90 is 1, sine 180 is
0.
Yeah, so it will be 0. So FCH is 0. And similarly, if you use the first and last expression, you will find FBC equal to FCD. So from this, what is your inference? You have this kind of a setup, three forces. You have FBC here, you have FCD here, and FCH here. Your inference should be FCH should be 0. And if FCH is 0, then FBC and FCD should be equal and opposite. So basically what I want to say is CH is a zero force member because FCH is 0. So do you find any of such member again anywhere in this picture? So you can look at the joint L. There same thing happening. KL and LM, they should be equal and opposite. And GL should be zero force member. You got what I'm saying, right? If so, then find similar link again. Any other joint. Are you guys getting what I'm saying? If not, please let me know, so I will explain properly. So you have a joint which has three forces. Let's say you have joint, you have three forces, basically three links are connected to it. Angle is like 90, 90
Sir,
and 190.
Yeah, IN is also the same.
Yes, IN will be a zero force member because you can see at the joint N, MN and NO, they are acting, they are joining parallelly, or they are on the same axis, and IN is a link which is joined to it in 90 degree. So in such a setup, the force on MN should be equal and opposite to the force on NO, and the force on the link IN should be 0. So if you think the force on the link IN is 0, then IN is a redundant link. then you can think of there is no in at all, only mn and no is acting, then it's a like a two force member, therefore should be equal and opposite for it to be in equilibrium. So that's the basic thing. This kind of setup, the perpendicular one will not take any load, the other two will take equal and opposite load, so that this three force member will be in equilibrium. I mean, this three force joint n will be in equilibrium. So basically now we have found the member GL, IN and CH are zero force members. So if you see options, I don't think fourth one is an option, correct option, because it has CH, but IN, okay, IN also it has OJ. Okay, OJ we haven't evaluated, but I don't think we need to evaluate. It's clearly not. So if you okay, anyway, we will go through OJ, what is happening at OJ. So O is here, J is here. Let's consider the joint O, that will be easier. You'll have support reaction here. So you'll have support reaction at O, then the force FOJ, then another force FIO, and then another force FON. Now what will happen is, you have a so I am just converting everything into horizontal and vertical components. So you have RO is a vertical force, FOJ is a vertical force, FON is a horizontal force. Now FIO is not horizontal or nor vertical. Let's assume this angle is theta. It can be any angle in generally. Here I think it's a 45 degree because everything is identical in length. But I am just taking general angle, some general angle. So I will just convert FIO into a horizontal component, FIO cos theta, and a vertical component which is FIO sin theta. Now we don't need FIO here because I have already converted that to horizontal and vertical forces. Now you can see we have two horizontal forces, FON and FIO sin theta. They are drawn in same direction, but they should balance each other. So FIO sin theta in magnitude should balance with FON. The vertical forces, three forces are there: RO, the reaction at O, FOJ and FIO cos theta. So in general, theta here, if you see, it's a 45 degree. You will find FIO to be OJ is the one that we want to focus on. So in general, FIO and ON will balance together. So FON is a finite value we have seen earlier, so that FIO will also be a finite value, it will not be zero. Now if you use that information here, FIO cos theta will also be a finite value, that along with the support reaction R0 should balance FOJ, that will not be zero in general. For specific cases it can be, specific numbers, like if you put some particular force combination, it will go to zero. In general, FOJ will not be zero. This is one way of arguing. So is that clear? Or any doubt in that particular session? So that's why I'm saying OJ will not be a zero force member, but we will have another zero force member. So if you see joint E, so remember where zero force members can appear. One is this kind of a setup, then this will be a zero force member. This both will be equal and opposite. Now another joint I am saying is E. If you see joint E, which will have two components acting like this. So we have FDE here and FEJ here, only two forces. There is not a third force, only two forces are here. Now if you see here, you can write the horizontal force balance equation, sigma Fx equal to 0. You will get FDE is equal to 0. And the vertical force balance equation which will give FEJ.
Both the forces will be zeros.
Yeah. So basically, both the forces FDE and FEJ both will be 0. So we are again finding two zero force numbers, DE and EJ. So this is another technique. If you have this kind of a joint, then both of them should be zero force numbers. An L kind of a joint. There is no external force acting. Now again, look at joint A. So joint A, basically it's an L kind of shape, right? But now there's a difference. It has an external force.
External force is acting.
Yes, external force P is acting. So it's not clearly a system like the joint E, but now it is a system similar to the first type, because you can see now it's an L kind of system. Though the links are not there, you can see here the P should be balanced with FAB. The external load P should be exactly equal and opposite to FAB. So I have drawn it in the other way. Doesn't matter. The magnitude should be equal and direction should be opposite. That's all. So FAB. So FAB should be equal to P, and FAF should be 0, because there is no vertical load acting at A to balance. If you write the equilibrium equation at joint A, you will find FAF being 0. Same argument as this case. You have 3 forces at a location. The forces are at 90, 90 and 180 degree. Then this kind of a situation should come. So you will find the force at member AF is also 0. So now you can see AF is 0, GL is 0, DE is 0. So option B is one of the correct option. Then CH is 0, EJ is 0, IN is 0. So total 6 of them included in option B and Z. So they are the correct option. Any question?
So is the second option is also correct?
Huh? Can you repeat?
No, sir. You mark the second option also as correct.
Yeah. Because both B and C both are correct, right? So it's an MSQ.
Yes, sir. Okay. I got it.
Yeah, it's an MSQ. So you'll have more than one solution being correct. Both B and C. Okay.
Yes, sir. Understood.
Okay. So, so this is another question. I think you can right now try it yourself. This is actually fairly simple. You have a stable and determinant system. You have 2 support reactions at C and 1 support reaction at A, and you have only 2 triangles, and you have to find the forces in links AB, AD and BD. So you can use either method of joint or method of sections or combination of both. It's fairly simple because you have only few joints and few links. Because we are running out of time, so I hope you could try it yourself. If you want, just take a screenshot. I will anyway upload this in Drive. Try to do it yourself. I will just tell the answer. So if you have doubt in this, just come next week and just ask me. I'll just tell what is the solution. So it's option C is the solution for this particular case. Okay. And so I'll move to the next problem. So this is another problem that you could try. So here you have joint A and C. So you need to find the net reaction force at B. That's a question. So from the question, so you can see B is actually a joint, and you don't have a you have to find what is the net reaction force at B. But usually when we consider, joint should be in equilibrium. We will say that the net reaction force or the net force at any joint should be 0 for it to be in equilibrium. So here then that is an issue, because we are asking for reaction force at B and there is no option saying it is 0. So I suppose, and I found some answer which is matching with option. So what I'm hope here is that if you look AB and BC, compare them, AB is looking like a rod and BC is a rope or a string. So I hope they're asking for what is the tension which is acting on the rope BC, assuming AB is a member. And also you can see 1000 Newton is acting on the member AB, which is not a truss system, because the force is not acting on a joint, it's acting on somewhere in the middle. So it's not a truss at all. We cannot consider this as a truss. You just need to take a section here, use the method of section, find the what is the equilibrium condition, find what is the tension. So that you will get it's 1333 or 34. You could try it yourself. Okay. And now I will touch up some problems which had confusion in the assignment. So in this problem, it's also like you cannot think this is as a pure truss system, because there is a distributed load acting over the entire BD. So there is an issue. What you have to ideally do is that 800 Newton. So we will come back to this kind of problems later, distributed load. But 800 Newton is the total force. It should pass through. It's a uniformly distributed load. This kind of loading is known as uniformly distributed load. This should pass through the center of mass through the loading, center of the loading, which is exactly the C. So you can think this is basically happening like this. The 800 Newton is actually acting at the point C. At point D and point B, there are no forces acting. Then you can fill the remaining. It will be something like this. And now if you see the member CED triangle, basically this member CD and ED will be zero force members, because you can see joint D, there are two forces which can be acting, FCD and FDE, which are at some angle, but there is no external force acting, so they should be individually go to 0. So they will be zero force members. So that is not the matter. We can continue the process and evaluate finally what is the force experienced by the member BG, FBG. So you can continue using method of joints from C, E, B, and once you reach B, then you can take the section like this, where you have FAB, FBG and FGF in the system. Then it's like just straightforward. Only the beginning thing you have to make sure that 800 Newton is actually passing through CE, that exact center. Why I wanted to take method of section here is that unwanted support reaction will be there if you otherwise take joint A or G. So avoid joints A and G. Just take the method of section, because both the joints are pinned joints. So we'll have 4 support reactions and 3 equations in the whole, so you cannot evaluate all those reactions. So avoid evaluating the reactions. Otherwise it's a fairly straightforward problem. So you'll find the answer to be also don't forget to use these particular values for root 2, root 3 and root 5. So your final solution will be let me check. Yeah, FBG you will get, it is minus 892 Newton in compression. So I can try this. Then another problem which created confusion is, in the problem 9. So you could try this. Basically it's a statically determinate and simple problem, just that one confusion was there. Option B saying there are two redundant members in the structure. So basically, confusion is that the redundant members here meaning zero force members. Okay. So when member has done no forces, basically we say it is not participating in the load taking process. It's like redundant in that sense. That's why we call zero force links or zero force members as redundant members. If I say that is the case, then it will be straightforward.
Sir,
Yes.
sir, the word redundant member refers to a link or just a point, sir?
Member means it's member, right? So it don't have any force. Internal force is zero. So I mean it's not
Yes, sir.
experiencing
For
any
that,
force.
for that a link, it refers to that link, right, sir?
Yeah, it refers to link. Member means link. Joint will be separate. Like you should say it's redundant joint. That is not the case. Joint cannot be redundant because joint anyway will have
Okay.
zero force totally. Net force will be zero. Member will also have net force being zero, but member will be experiencing equal and opposite forces on both sides. It will be in equilibrium. But a zero force member means that there is no force at all acting on it. So,
Okay.
any clarification?
No, sir.
So basically, if you have a member, you will have equal and opposite forces, either compression or tension will be acting on it. So net force will be zero always in a member. So if I say BF, net force will be zero. But just that it is acted by equal and opposite forces on both sides, either compression or tension. According to which, right now we are considering rigid bodies, but this is important in deformable bodies. That is a real case, right? Because there is no rigid bodies exist in real world. Deformable bodies subjected to an external equal and opposite forces will be in equilibrium, but they will have deformation. They will compress, or they will have a tension, or they will have a compression. They will deform. That is we will learn in solid mechanics or mechanics of solid subjects and all. But if there is no force, then it's a redundant link. There is no force at all. So it's a zero force member. Then there will not be deformation also. So that's why this has some particular. I mean, it's not taking any load. So here you can see the joint G. If you just consider joint G, you can say GB will be a zero force member. And if you just consider joint E, you can say CE is a zero force member. So they are redundant in that sense. I hope that is clear. And in the question 10, okay, I mean this is not question 10 in the assignment, I think question 1 in the assignment. So here, yes, there is some, anyone find any issues here? So there are some issues. I mean the options says truss 1 and 2 are the correct answer for the system, but I think it is not. Truss 3 is the correct answer. So I have asked them to reevaluate it using truss system 3 as the option, because basically it's asking for stable and statically indeterminate. So option 1 you can say it is not stable at all, because if it is a triangle is here, it will be stable. See, you can formally evaluate these things using number of joints and number of links and number of external forces, internal forces. But I am just looking at this, and from the how many triangles present there, I am just telling. So you have only 3 support reactions here. So externally it is determinate, internally it's unstable, because this link will make, it's a chain, kinematic chain, so it will not be a structure. So 1 is not the answer at all, it's not stable at all. 2 is stable, but over constraint you will have 4 unknowns. So it is statically uh, stable, and yeah, 2 is also but okay, 2 is internally determinate but externally indeterminate. So I think 2 also can be an answer. So it's statically indeterminate anyway. I hope you agree with that.
Sir,
Yeah.
sir, sir, one down, sir.
Yes.
Sir, I know how to find that statically indeterminate or determinate.
So statically indeterminate means that basically we are doing the static analysis. Indeterminate means that anything which we cannot find it explicitly. For example, here all the internal forces you can evaluate because it's only triangles. So you just need to do the joint equations for every joint, equilibrium for every joints. You will be able to evaluate all the internal forces. Just that when you come to the external forces, the support reactions, the reaction here R1, R2, R3, R4. See, these are all pin joints. You will have 2 support reaction in each. So 4 reactions you have, and you have 3 equations: sigma fx equal to 0, sigma fy equal to 0, and sigma m equal to 0. So with that you cannot evaluate R1, R2, R3, R4, 4 of them completely. You can evaluate 3 of them. The fourth one will be always an unknown, which we cannot determine, which is indeterminate. So in that sense it's externally indeterminate. Internally it's determinate, but in overall sense it is indeterminate, but it's stable. Hope that is clear.
Yes, sir, understood, sir.
Yeah. Now we'll come to 3 later. Let's see what about 4. So 4 is stable. You can see only triangles, and you have 2 reactions here and 1 reaction here, 3 external reactions, 3 external equations. So all of them are determinate and is stable. So it's statically determinate and a stable system, but we are asked to find whether it is statically indeterminate or not. So 4 is not the correct answer. Now we come to third. Third will have 2 support reactions here and 1 reaction here, and 3 equations. So all the external reactions are determinate, and the structure is stable. You can see only triangles, but I would say it is a superstructure. It's an over constrained system. Basically you have simple triangle here and simple triangle here, and you can think this is a simple triangle and this is a simple triangle. Now you have one extra link here. That extra link make it a superstructure whose reaction whose internal forces you cannot find. That you can just use n in 2j minus 3 to check. You will find number of links are greater than 2j minus 3. It's an over constraint. So the reaction in these members, this and this members, you cannot explicitly evaluate. One extra variable is there. So it's an statically, so it's internally indeterminate. External forces are determinate, internally indeterminate. So 3 is indeterminate, but it is stable. It's actually super stable. It's a superstructure. So 3 is such an answer, and I think 2 is also an answer. So, but it is stable. It's externally indeterminate. So I will ask them to reevaluate with these options.
Sir, 2 is not correct answer, sir, because internal redundancy is not present.
Yeah, internal redundancy is there, so not there. So it is internally determinate, but externally
Statically indeterminate with internal indeterminacy, but internal indeterminacy is not present in 2.
Yes, that is true. So internally I agree it is internally determinate, but externally there is an indeterminacy present.
So I think only 3 is correct answer.
So in that case 3 is already correct, I know, but only confusion is whether 2 is correct or not. So I will discuss this with sir and come to a final conclusion. I hope the point regarding 2 is clear to you, that internally it is determinate, but it has an external indeterminacy. So I don't know how
Sir,
to.
the question is statically indeterminate with internal indeterminacy. It is the internal redundancy.
Oh, okay. Sorry. Yeah, I didn't notice that. Yeah. Then you are correct. Then only option 3 will come. Yes. So if I didn't notice that it is specified the internal
Okay, sir.
redundancy.
Okay, sir. Okay.
Yeah. Okay. Sorry. Thank you for pointing me that. So internal redundancy. Okay. In that case, figure the trust system 2 will not be the answer. It has an external redundancy or indeterminacy, but not the internal one. So in that case, option 2 will not be correct. So only trust system 3 is the correct answer. Okay. Uh, yeah, that's all. Any other doubt, questions?
No, sir.
Okay. So then we will meet next week. Thank you.